So once I know how to do half reactions, I can do my full reactions between metals and nonmetals. I have to show work, show all electrons, right? So it actually involves those half reactions that we talked about. So again, my magnesium, my phosphorus, right? If you're given this prompt, you'd have to show work for each thing. Magnesium has these two electrons that need to be lost in order for it to be stable, in order for it to be happy with that +2 charge, right? And phosphorus still needs to gain 3 electrons, just like on that last video, so that it can be happy and be this phosphide ion that has a -3 charge. We'll talk about that name phosphide later. But in order for this to work, in order for magnesium and phosphorus to react, you have to have the same number of electrons being lost as gained, right? And I have 2 electrons being lost by magnesium and 3 electrons being gained by phosphorus. I need to have the same amount of electrons being lost and gained. So I actually have to balance this, right? Which, if I multiply this top row by 3, so there's 3 magnesiums here, 6 electrons being lost, and 3 magnesium ions that are being formed, right? I could balance that out with 2 phosphorus atoms that are losing or gaining 3 electrons apiece, because that'd be 6 electrons total, right? I use that least common multiple idea. Between 2 and 3, I need to get to 6, right? As long as the number of electrons are the same being lost and gained, right, you can get a balanced reaction, right? That down below, if I do this in terms of adding these 2 half reactions together, right, I actually have 3 magnesiums here, but each one of those magnesiums had 2 dots, and 2 phosphorus atoms here, each one having 5 dots, and they're going to react together to make 3 magnesium ions that have no dots, and 2 phosphide ions that have 8 dots, right? So I actually have all electrons accounted for in this reaction, in this overall reaction. It's balanced, right? 3 magnesiums have 6 electrons to lose. 2 phosphorus atoms need to gain 3 electrons apiece. That's 6 total, right? Before and after, all electrons are accounted for, empty and full, because phosphorus gained those electrons, magnesium lost those electrons. But this is how you create that balanced reaction. You use 2 half reactions and combine them to get this full reaction. The whole idea was that, okay, I multiplied that 3 through, and I had 6 electrons here, and I'm multiplying this 2 through here. The 6 electrons lost cancels out with the 6 electrons gained, so this is balanced, right? So that's the math version of this work. Now you could actually do it a different way, right? I told you before, if you want to show your work differently, you just have to be able to be a little bit more creative. You might need a different color. Now, again, I'm going to force you to use a different color if you want to do the work this way, but if it makes more sense to you this way, do it this way. Magnesium and phosphorus need to react together. The other version of this work that I would allow you to do is a little bit more visual, but again, I'd like to see a different color, because I'm going to take this electron here and I'm going to move it. I'm literally going to move it from there to there, so that this magnesium lost an electron, that phosphorus gained an electron, right? And then I'm going to take this electron here, move it over to this side. Now that phosphorus has 2 more electrons than it started with, and this magnesium lost 2 electrons, and this magnesium is now happy. It has a charge. It's got that +2 charge. Problem is, the phosphorus isn't happy yet, right? So this is a visual version of this, and it's perfectly fine if you want to use this, but you have to go back and forth between colors, because in order to continue this, I need more magnesiums, because I need to lose more electrons so that that phosphide ion can be formed, right? This electron could be used to make this final pair here, to make this phosphide ion happy with that -3 charge, but now the magnesium's not happy. It needs to lose one or more electrons, so I need to bring in another phosphorus. And I just keep doing that until I'm done. Because eventually, as I continue to do this, as I bring electrons from one thing to the next, and always put a charge next to that ion when it's happy, because then you know you're done with it, right? Plus visually I can see that you understand that each of those things gained or lost to become that charged particle, right, that ion. But this phosphorus needs 2 more electrons, so I'm going to need another magnesium. And when I finish off this part of the picture, once this magnesium loses these 2 electrons to make this phosphorus happy, you should be able to see that I have the exact same result as I got in my math version originally. I still literally had 3 magnesiums that had 2 electrons apiece that reacted with 2 phosphorus atoms, each one having 5 electrons, and the end result of my reaction is that I had 3 magnesium ions, each one having a +2 charge. And I had 2 phosphide ions. Remember, you got to put dots all the way around a negative ion, because that represents 8 electrons total. It's full. There would actually technically be dots around this magnesium, right? It reverted to an inner shell that's full, but we're only dealing with valence electrons right now. So before and after, I got the same answer as I did before. You still need to write out the answer the same way as I did in the math version, but if this work makes more sense to you, do that work. Some people are more comfortable that way. I just like to see color, right, when you're doing it, or else it's really hard for you to keep track of what's going on, right? You can't really see the before and after in your work, right? But I can see with these arrows, and those arrows have arrowheads pointed in a specific direction. That tells me that the electrons are moving from the magnesium and going to a phosphorus. That's important. If you don't do that in your work, I can't see that. You can't just have lines that connect dot to dot. That's a different kind of work that we'll use later. But you can choose which style of work you want to do, and it may just depend on the example that you have to do. If I have to do potassium and sulfur, right, like on this next slide, I know that potassium just has that 1 valence electron, and that sulfur has 6, right? I could probably easily, quickly write this version of the work to make this potassium happy. It's got a +1 charge, right? I'm going to need 1 more potassium because that sulfur is not happy yet. Excuse me, not supposed to make extra dots. Now that sulfide ion is complete, potassium's happy, so I'm done, right? Sometimes this is a short version of the work, right? But that doesn't mean that it always makes sense for you, right? You still have to write out the end result. I had 2 potassiums, each one with 1 dot to start with, and I had 1 sulfur atom with 6 dots. They reacted to make 2 potassium ions with a +1 charge and 1 sulfide ion. Again, sulfide's got electrons all the way around, and it's got a -2 charge. But you can show the math work, or you can show a more visual version of that work. I don't really care. I personally like how the math works out. I kind of like that better. It's more organized. It's not as sloppy, right? So I prefer to do it that way, usually. It just depends on the person. Tin's going to lose, remember, because it's a metal. So losing 4 electrons can give me a tin with a +4 charge. And then I have bromines, each of which have 7 valence electrons. Finish that off there. And they're each going to gain 1 electron. Probably don't need that 1 if you don't want to put it there. So that you can make this bromide ion with a -1 charge. I personally kind of like to just show my work. I need 4 to multiply through here so that the electrons cancel out. And then I have 1 tin, literally, combined with 4 bromines, 7 dots, to give me 1 tin ion that has +4 charge and 4 bromide ions. So it really just depends. You can pick and choose when you want to do it, because I could actually see how that would benefit you. Either way, you have to give me the same end result. You have to show a reaction with 2 reactants and 2 products. The reactants are regular atoms with all of their valence electrons, and then the products, right, have more or less valence electrons than they started with, and they're ions. So however you want to show your work, do it. But pick a way. Remember, if you're going to do the visual version, you have to use color, right? So you can't just have pencil for everything. You could use pencil and pen. So even if it's a black pen, I should still be able to tell the difference between the pencil mark and the pen mark. So use color, use a pen, whatever you need to do. But show your work, right? I can show that these are balanced reactions, that the same amount of electrons are gained and lost, and that's how I know that they're balanced, right? Okay, so that should be good for this video.